This is second part of our discussion of power functions and root functions. Now remember that we started our discussion by taking n is equal to 2. In other words, we studied what are square root functions and principal root functions. And we also studied that when we apply the mapping f of z is equal to z square, then the vertical and horizontal lines in the z plane becomes parabolas in the w plane. Now we are going to choose some other curves in the z plane and study the behavior or the effect after applying the mapping z square. Now these curves are basically hyperbolas. Now we start from the hyperbolas of the form x square minus y square is equal to c1. So they are hyperbolas of the form this, okay, or of the form where the branches lie along this y-axis. Now what is our claim? Our claim is that these two branches of the parabola are mapped in one-to-one and onto manner onto this vertical line x is equal to c1. Okay, so this is our claim. Now let's see how to prove this claim. Now from x square minus y square is equal to c1, we can calculate the value of x. So there will be two values, x is equal to plus minus and square root of c1 plus y square. Now this c1 is a real number, y is a real number, and this is square root of a real number, just as we used to calculate in our schools. Okay. Now using this value of x in the value of v, so now remember v is equal to 2xy. So using this value of x in v, so it becomes v is equal to plus minus 2y square root of c1 plus y square. Now if we consider the value of x to be positive, then we will get the following curve, which we will later on see that it is in fact a straight vertical line. Now u is equal to c1 and v varies in the following way: 2 into y and square root of c1 plus y square. And if we use the negative value of x, so it becomes the following line: u is equal to c1 and v is equal to minus 2y square root of c1 plus y square. Now let's study these two images separately. Now consider the first case where u is equal to c1 and v is equal to 2y square root of c1 plus y square. Now this is of course image of the following parabola. Okay, so let's say this is the parabola x square minus y square is equal to c1. Now the image is a curve for which u is always constant c1. Okay, so if u is equal to c1, then it is this point. Okay, so u is equal to c1. So of course it is going to be a straight line because u is always constant. Now let's see what will happen if v is equal to 2y square root of c1 plus y square. Now in this case, as y varies, okay, so remember in this case x is positive, so basically we are considering this portion of the hyperbola, okay, where x is positive. The negative case correspond to, so this is x positive, so this is the case when x is negative. So now we are considering this case, this blue portion of the hyperbola. Now this blue portion is mapped onto this line, and we can see that when y increase from for example negative value, if y is negative then v is negative, so we are on the negative side, and when y varies or increase to positive values, then v again become positive. So in other words, if we travel in this direction, then we will be traveling in the same way in the w plane. In other words, if we travel on this portion of the hyperbola from bottom to top, then we will be traveling from bottom to top on this vertical line. Now let's see what will be the effect of or the image of the second portion of the hyperbola. So this is the portion where x is negative. Okay, now this portion will also be mapped onto u is equal to c1. Okay, so which is of course a vertical line, u is equal to c1. Now let's see what will be the effect of the value of this v. Okay. Now in this case, v is equal to minus 2y square root of c1 plus y square. Now we can see that when y is positive, then v is negative. In other words, if we are here, somewhere over here, where y is positive, then v is negative. V is on the opposite side. And if we travel to the negative values of y, and when y become negative, then v become positive. So in other words, if we travel from top to the bottom on this portion of the hyperbola, then we will be traveling from bottom to the top on this line. Okay, so that's the effect or the image of this hyperbola under the mapping f of z is equal to z square. So both portions of the hyperbola will be mapped onto this straight line, but the difference is only that this portion, if we travel in this direction from bottom to top, then it will be mapped onto this line traveling from bottom to top, and on this portion, if we travel from top to bottom, then we will be traveling from bottom to top in its image. So both portions are mapped onto this vertical line. Now let's consider other kinds of hyperbolas. Now these are hyperbolas of the following form. Okay, so their graphs are in the z plane. Okay, so in the z plane, they are hyperbolas of the following form. Okay, now let's see how to calculate their images in the z plane under the mapping f of z is equal to z square. Now we know that v is equal to 2xy, and if this 2xy is equal to c2, then we get v is equal to c2. So the coordinate v is always constant under this map. And what will happen with u? So if we take, or if we use y is equal to c2 over 2x, and using this value in u is equal to x square minus y square, we get x square minus c2 over 4x square, c2 square over 4x square. And of course, v is equal to c2. Now let's see what does it mean geometrically. Okay. Now remember, our hyperbola is of the form this one and this one. Once again, it has two portions. Now let's focus ourselves onto the portion in the first quadrant. Okay. So this red portion. Now v is equal to c2. So in other words, this is always a straight line. It's basically a horizontal line. Now what is the effect of the values of u? Okay, so how u varies. Now we can see that when x is very, very small, okay, so if we are very, very close to the origin, okay, somewhere over there, then basically it is negative. Okay, so if x is small, then this number is very, very small, and since this x square is in the denominator, so that's why this number becomes a very large number in the negative, with negative. Okay, so that's why this u is a very, very large negative number. Okay, so that's why we will be somewhere over there. Okay, so when we get very, very close to the origin, then we will be on the very, very far away from the origin, but on the negative side. Okay, on this line. And when we travel in this direction, and the values of x increase, and when x becomes, for example, let's say 100, then this 100 square will be a very large number, and since this 100 is in the denominator, so it will be a very small number. So in general, the value of u will be some very large positive number. So in other words, if we are traveling, okay, not at 0, but very, very close to 0, so if we start our travel from this portion, okay, so in other words, we are traveling from this side. So these numbers are very, very so has x coordinate which is very, very close to the origin. So when we are traveling from this side, then in the w plane, or after applying z square, we are traveling in this direction. Okay, and similarly we can calculate the other portion, the image of the other portion. So let's just focus ourselves onto this green portion of the hyperbola. Now in this case, once again, the value of v is always fixed, which is equal to c2. But what is the effect of this y? Now, when y is a very, very large number but with a negative sign. So in other words, if we are somewhere over there, okay, then this is basically a negative number. Okay, so for example, if y is equal to minus 100, so this is a very large number, and this is a very small number because we are taking the square of y as well. So we will be somewhere over there. Okay, and if we travel in this way, and y becomes a very, very small number, because for these numbers correspond to values of y which are very, very small. So when y becomes small, then this number becomes very, very large, and so that's why if we travel in this way, then in its image under the mapping f of z is equal to z square, we will be traveling from left to right. So in general, we have the following picture. So if we travel in this way, we will be traveling in this direction. If we are traveling in this way, we will be traveling in this direction. Similarly, if we consider these hyperbolas, so if we travel from bottom to top, then we are traveling from bottom to top. But on this portion, if we are traveling from top to bottom, then we will be traveling from bottom to top. Okay, so in general, if we have these hyperbolas, then these red lines, okay, so remember, these red lines will be mapped onto these vertical lines, and these blue lines, so they will be mapped onto horizontal lines. So this is the effect of applying this mapping z square onto these hyperbolas. Now let's start the discussion on the geometry of the map f of z is equal to z raised to power 1 by 2, or the principal root function. Now to be very honest, it is not going to be very complicated, because it is just the opposite of the geometry of z square. So whatever z square does to the subsets in the w plane, z raised to power 1 by 2 does exactly the opposite of that map z square. Okay, so once again we are going to use the polar coordinates, and if z is equal to r e raised to power iota theta, then f of z is equal to z raised to power 1 by 2 becomes the following element. Okay, so r raised to power 1 by 2 e raised to power theta by 2. Now once again, if we use the same exponential form in the w plane, then this map, this principal root map, can be defined using these equations. So r square and theta by 2. Okay, so for example, if we have the following complex number, so for which r is equal to 1 and theta is basically 60 degrees, then if we apply f of z on this complex number, then we get a complex number for which theta is equal to 60 by 2 degrees, in other words 30 degrees, because it will be halved. And if r is equal to 1, then square root of 1 is 1, so that's why rho is equal to 1. Similarly, we can calculate the images of other complex numbers under this mapping, under this principal root mapping. Now, if we restrict our domain of this principal root function to the following set B, which is set of all complex numbers in the z plane, for which this modulus lies between 0 and 1, and theta lies between minus pi and pi. So in other words, it is this unit disk. Okay, so we have colored this unit disk just to observe that what will happen with these colors, with the complex numbers lying in these shaded regions, when we apply this mapping f of z is equal to z raised to power 1 by 2. Now we can calculate the image. So in this case, r lies between 0 and 1. So when we square root, then rho lies between 0 and 1. And when we apply this principal root function, theta will be halved. So in other words, phi lies between minus pi by 2 and pi by 2. Okay, so once again, this minus pi by 2 will not be included. So this is dashed line. And we can easily observe that these complex numbers lying in this green region will be mapped onto complex numbers in this green region and corresponding to other colors. Of course, if we apply z square, then this half unit disk will be mapped onto full, and if we apply this principal root function, then this full disk will be mapped onto this half disk. Okay, and similarly, we can observe that, okay, so remember when we applied z square on the hyperbolas, then they become horizontal and vertical lines. Now, of course, if we apply this principal root function onto straight lines, okay, straight vertical and horizontal lines, then we should be able to get hyperbolas. Now, I am going to leave this fact as an exercise for you, and this is exactly the opposite of the case that we studied for this z-square map. And similarly, remember, we proved that if we apply z-square onto vertical and horizontal lines, then we get parabolas. And we also studied their structure. Now, I'm going to leave the opposite fact as an exercise, that if we are given parabolas and if we apply this principal root function on them, then we should be able to get this vertical and horizontal lines. So this is the end of our discussion on the geometry of z-square and z raised to power 1 by 2 functions. We'll continue our discussion in part 3, where we will study the geometry of more general functions, which are z raised to power n and z raised to power 1 over n.